In a previous video on populations and samples, we posed this scenario where a statistics exam was given to 100 students, divided up into 5 classes of 20. And we were able to use the language of statistics to describe that situation in more detail. For example, we now know that we could call the whole school in that scenario the population. And one of the statistics classes could be called a sample. We also know that we could collect different types of data for the exam results, some that may be quantitative, like the exam scores, and others that may be qualitative, like perhaps their teachers' names. And we went into a bit more detail of different types of data at the time with things like ordinal versus nominal data, but that was the gist of it generally. What we did not do, however, was actually answer the core question that was posed. The core question that a school or group of teachers would be likely to have if they just gave their whole school an exam, which is, how did the students actually do? To answer this, we could start really simply and just make a list of all of the scores. Here are the 100 scores written out. We could read through them and get a feel for what kinds of numbers we're seeing. And this could totally work. If we had a really small number of tests, a really small sample. But even at 100, listed out like this, it feels like a lot to read through. And what if we had 1,000, 10,000, or even 1,000,000 test scores that we had to sort through? You can imagine this process would get extremely unwieldy extremely quickly. So we're gonna need some ways to summarize. Before we get into any complex computations though, I'm sure you've heard the cliche that a picture says 1,000 words, right? Well, a picture can say 1,000 data points too. So visualization is going to be a really powerful tool that we can use to help us summarize data sets. One really common way you'll see this done is to use a histogram. Here we have a histogram of exam scores for 1,000 students. As you can see, it's essentially just a bar graph for quantitative data. We can list different numeric scores, or groups of numeric scores, in order along the bottom, and count how frequently they occur along the side. To be a bit more specific, notice how on this graph, each bar counts continuously in order starting from 28 and going up to 100 without skipping any values in between. Like, any of these adjacent bars don't skip numbers. They go 78, 79, 80, not something like 78, 80, 81, with a missing 79 in between. This is true for when values are grouped too. Notice how this group here goes from 80 to 89 and then starts right at 90 in the next group. That's generally good practice for making a histogram. The key characteristic though that identifies a histogram is going to be the height of the bar indicates the frequency, or in our case, it indicates how many students got that score on an exam. For example, we can see that 35 out of the 1,000 students scored a 78, 20 scored a 90, and 67 scored a 100. These types of charts can be really effective for painting a picture of the data. And in our case, we can much more clearly and much more quickly get a sense of how the students did on the exam than if we just listed out 1,000 test scores. But there is a little more nuance to pay attention to here. For example, I've already shown you 2 different variations of a histogram that use the same data. Now, naturally, I've modified these charts to be different on purpose for the sake of this example. So this one on the left counts each exam score individually, where this one on the right counts them each in groups. Like all of the scores from 80 to 89, for example, are counted together here. But what's really important to note is that the stories these 2 graphs tell can be drastically different despite representing the same data. This one, for example, highlights that the most common score, the score with the highest bar, was actually a 100. But on the other graph, a score of 90 or higher is shown to be one of the least common scores, certainly not as frequent as the scores in the 70 to 79 range, and so says nothing about the students getting perfect 100s. What we can take away from this is that the way we set up our charts can have really meaningful consequences and greatly impact the story that your charts can tell. Therefore, it's going to be important for us to carefully consider these details, both as someone who will be creating these charts, as well as someone who might be interpreting them. Let's break down these characteristics a bit further. First, each of these groups that we've split our data into is typically called a class, or sometimes a bin. They can be defined from a minimum value, called the lower class limit, to a maximum value, called the upper class limit. You'll usually want to set them up so that they are the same length too, right? So you don't have one bucket that's like from 50 to 90, and then one bucket that's just like 90 to 100. We would want to be consistent, like 70 to 79, 80 to 89, 90 to 99. We call this length the class width or the bin width, which you can compute by taking the difference between the lower limits of two consecutive classes. Using our example here, we could subtract the lower class limit of 70 from the lower class limit of 80 to get a bin width of 10. Now, another term you'll hear often that sounds kind of similar is range. Range is distinct from class width though. If you recall back to when I first introduced this graph, I described it as starting from 28 and going up to 100. That full width from the minimum value to the maximum value of the whole data set, that's what we call the range. So in our case, the range would be 100 minus 28, which is equal to 72. One other number that might be worth noting for each of these classes is the midpoint, the number in the middle between the lower and upper class limits. In some contexts, you might even describe a class based on its midpoint value rather than its width, but either way, it's going to be a pretty straightforward formula to find it. Basically, you just add the upper and lower class limits and divide by 2. So for example, our class that spans from 70 to 79 would have a midpoint of, well, 70 plus 79, which equals 149, divided by 2, which gives us 74.5. All right. So how do we get a sense for how our school of 100 students did on the statistics exam? Well, we summarize. Typically, visualizations like histograms would be the most effective way to do this, but you may see some other variations of charts or even tables that aim to achieve the same idea. These types of summaries in general are what we call frequency distributions. Understanding how data is distributed is a major part of statistics and data analysis. So using and visualizing frequency distributions in this way will be critically important to our study of statistics. Now, there can certainly be much more to this story, and as you continue to study stats, you'll get familiar with a variety of different ways that data can be distributed, what that tells us about the data, and different tools that we can use to analyze them further. But for now, hopefully you've got a sense that using a frequency distribution and visualizing data via histograms can be a powerful way to summarize that data. And if we carefully consider the details, like how we set up our classes, we can craft our charts in a way that can be helpful to support the stories that we aim to tell with statistics. As always, I hope this was helpful. If you have any other questions, let me know in the comments below. But otherwise, I hope you have a great rest of your day.